All right, let's see, I'll make it a little bigger still. Or will it not let me? Okay, apparently it will not let me make it bigger than this. People in the WebEx meeting, is the text readable? Please let me know. Okay, great. All right, so major technical difficulties down here. We've lost half-hour class time, only have 45 minutes left. So what I'm going to do is I'll start covering what was intended for today. And so I'm willing to stay past the end of class time, but that's up to everyone else. Okay, and then those two students who are here in Gulf Park, once class ends, I will stick around for any questions or all right, because it's like here for you guys. So sorry about the okay. So now we're getting into a new chapter 7 on the problem of polynomial interpolation. So the problem that we're looking to solve in this chapter is, given a set of points in the xy plane, find a polynomial that passes through all of them. Now, the simplest version of this problem you're already very familiar with from much lower level math classes. Given 2 points, find the equation of a line that passes through them. So this is just a generalization of that to more points. For example, if you have 3 points, find a quadratic that fits them. If it's 4 points, a cubic, and so on. So in general, if you have n plus 1 points in the plane, so denoted this way, x0, y0, x1, y1, etc., find a polynomial of degree n. So however many points you have, polynomial is of degree 1 less than that. And that passes through those points. In other words, when you substitute any x value, any of these x values into this polynomial, you will get the corresponding y value. So Pn is called the interpolating polynomial for this data. So, and like I said, if n equals 1, you already know how to do that. So as an example, if n equals 3, we have these 4 points that we like to fit. So what's a cubic that passes through them? So the most straightforward way to solve this problem is just to set up a system of linear equations. So here is our polynomial with unknown coefficients, A0, A1, A2, A3. So what we do is we substitute each of the x values, x0, x1, x2, x3, into this polynomial, and we set them equal to the corresponding y values. So what we have here is a system of 4 linear equations in these 4 unknowns, A0, A1, A2, A3. So we can just go ahead and solve that by whatever means, like what you learn about in Math 326. Gaussian elimination, or if you're in MATLAB, you can be using backslash to solve it. In fact, for polynomial interpolation, that's what MATLAB's function polyfit actually does. It can be shown that if the x values are all distinct, and for now we will assume that they are distinct. We will drop that assumption later in the chapter. But if they are distinct, then the matrix of this system, which is called a Vandermonde matrix, can be proven to be non-singular or invertible. Therefore, this system of equations does have a unique solution. But this is actually not a good approach. For one thing, solving a system of equations, of n equations and n unknowns, in general, takes on the order of n cubed arithmetic operations. And we can do better than that. The methods that I will show you later for solving this problem and getting these coefficients can be solved in order n squared operations, a whole order of magnitude less. Also, if any of the x values are close together, the system of equations is ill-conditioned. So the condition number of this problem of solving a system of equations can get very large in that situation. So the So the result, the coefficients can be very sensitive to rounding errors. So although this is the most straightforward approach, it's really not the best one from a numerical standpoint. In terms of two of the three criteria, efficiency and robustness. So there are different approaches that we can take. I'm just going to talk about one of them today, and that's called Lagrange interpolation. Now, the way that the polynomial, sorry if I'm going to go back for a minute, the way a polynomial was written before, this is the standard form that we're accustomed to for most situations. This is called power form, where you just have a linear combination of 1, x squared, x cubed, and so on. We're going to write the polynomial differently to obtain a more efficient method of computing the coefficients. So Lagrange form. So the polynomials express a linear combination of these polynomials that are called Lagrange polynomials for the given x values. And then the coefficients are just the y values that you're given. And the reason why that works is the Lagrange polynomials are designed so that if you have, because what you have is you have a sequence of polynomials. You have ln0, ln1, ln2, and so forth. You have n plus 1 Lagrange polynomials in total of degree n. So you, if you substitute the x value I into polynomial j, then you'll get 0 if I is not equal to j, and it's equal to 1 if I equals j. So if I substitute any x value into this equation here, so if I substitute xi, then all of these terms will be 0, except for the one when I is equal to j, in which case the result is yi. So in summary, you substitute in xi, you get yi, which is what's intended. Okay. So for the example that I gave earlier, with this data, my y values are 3, minus 4, 5, minus 6 for these points, minus 1, 0, 1, 2. So my polynomial that I'm looking for has this form. So I've substituted the y values, 3, minus 4, 5, minus 6, as coefficients of the Lagrange polynomials, L30, L31, L32, L33. Now, I'm going to show you how to get the formulas for these four Lagrange polynomials. So we'll start with this one, L30. So the idea is that if I plug in x0, I want the value to be 1. And if I plug in any of the other x values, I want to get 0. So these are the conditions that the first Lagrange polynomial has to satisfy. And then here are the conditions for the others. So notice in each case, if you substitute any of these x values, minus 1, 0, 1, 2, you get 0 in all cases except 1. So these are the situations that I'm indicating right here where you get a value of 1. So if we look at what's happening in this first column, the Lagrange polynomial L30 has 0, 1, and 2 as roots. So this should be included in the factorization, x minus 0, x minus 1, x minus 2. That ensures that it has those 3 roots. But now when you plug in x equal to minus 1, if I substitute that up here, I'm not going to get 1. Whatever I do get, though, I'll just divide by it. That way the fraction as a whole is equal to 1 when I substitute x equal to minus 1. And the same thing, like if I move to the second polynomial, L31, the root should be minus 1, 1, and 2. So that it takes this factorization, x minus a minus 1, x minus 1, x minus 2. And then to ensure that when I plug in 0, I get 1, I plug in 0 up here and divide by it. So you can see the pattern in how these Lagrange polynomials are to be constructed. This is a general formula right here that for polynomial number j, I'll have linear factors of a form x minus xi for I not equal to j. That guarantees that if I substitute xi where I is not equal to j, one of these factors will be 0. Therefore, the whole expression will be 0. And then when I substitute x equal to xj, I would get a product of factors xj minus xi up here. So I divide by those same factors to ensure that I get a overall value of 1. Okay. Any questions about Lagrange polynomials? Okay. Now, getting the interpolating polynomial in MATLAB is quite easy to do. You use the function polyfit. So the way you use it is you pass in a vector, row or column vector of x values, vector of the same dimension as the y that holds the y values, and then you get to specify the degree. Now, what I've shown here is only for a case of having n plus 1 points, and then you get a polynomial degree n. So then the degree would be n with the assumption that x and y have length n plus 1. And remember from the MATLAB tutorial, the polynomials are represented in MATLAB as a row vector of the coefficients from highest degree to lowest. And that's what will be returned here. So it'll return the coefficients of that interpolating polynomial in power form. Remember, the interpolating polynomial is unique. Doesn't matter whether you solve a system of equations from earlier or Lagrange polynomials. The polynomial you'll actually get is the same no matter what. So if you use this command where n is equal to the length of x minus 1, then you'll get the polynomial. Now, it's not a great way to get it. It solves a system of equations involving a Vandermonde matrix. Okay. All right, so the question I see in the chat. Okay, so I think if I understand you correctly, what you're asking is, if I were to take the polynomial Lagrange form and like basically expand it and gather-like terms and all that, yes, you do get that formula. So in other words, yeah, if I solve this system of equations and get the power form coefficients directly, or if I compute the interpolating polynomial in this form, but then convert to power form, yes, you will get the same polynomial. Yes, and that comes from here, the knowledge that a matrix of this system is can be proven to be invertible when the x values are distinct. So yes, it is unique. So really, the contrast we're looking at here is we can always get it this way, but that's not efficient. So this would be more efficient. And also it gets around the sensitivity to round off errors because we're not solving a ill-conditioned system of linear equations. Although, in my opinion, this is actually still not the best method for obtaining the interpolating polynomial. Really, the most efficient method is Newton interpolation, which is what I'll cover next week. But the Lagrange form is still useful for certain applications. So it's still of importance. Now, so even though we're not incurring order n cubed operations to construct a polynomial in this manner using Lagrange polynomials, the problem is with the Lagrange polynomials in its factored form, if we want to evaluate the Lagrange polynomial, that's still not very efficient because for a polynomial degree n, I'm still performing order n squared arithmetic operations just to evaluate these Lagrange polynomials. So Lagrange form is not ideal for evaluation, but there is a better way. So still working with Lagrange form. And what's interesting is this is actually a relatively recent development, so not even 20 years old. An approach to working with Lagrange polynomials that allows for more efficient evaluation, and it's called barycentric interpolation. Okay. So what you do is you compute these quantities that are called the barycentric weights, and all we have here is this is the denominator of each Lagrange polynomial. Because notice we have xj minus xi, all those factors multiplied together, and we actually saw those in this formula right here. So we're just taking the denominator. So we go ahead and compute these just one time. Now, this still occurs order n squared operations to get all of the weights, but it only has to be done once, and then you can reuse them. This leads to another way of writing the Lagrange polynomial. So if I define pi n of x to be this product of x minus each of the interpolation points, so there are n plus 1 factors overall, then I can write the Lagrange polynomial as this product, but then I divide out x minus xj, so it cancels with the x minus xj in here, and then I include the weight. So this formula is equivalent to the Lagrange polynomial formula that I showed you earlier. Now, the reason why this is helpful is if I now write out my Lagrange interpolating polynomial, remember from before, it's a sum of the y values times Lagrange polynomials. But this part, this is the key. This part does not depend on j. So you can factor out of a sum. And that's what's done here. Okay. Now, this is for a general polynomial. What about interpolating the function y is equal to 1 for all x? Well, now I just use this formula again. But I have 1 over here, and then my y values will all be 1. So now it's just this. So this is the specialization of this equation for a case where your polynomial is equal to 1. Now, if I take this equation and divide both sides by this equation, I have p n of x on the left side, and then I divide these two, and look what we have here. The pi n of x cancels out. And now you have this. So this is the value of the Lagrange interpolating polynomial, as long as x is not equal to any of the interpolation points. So you can't use it for those points because you'd be dividing by 0. But if x is equal to one of the interpolation points, you know what the value is supposed to be. It's supposed to be the corresponding y value. So for all other x's, you can just use this. And once you've computed the weights, you do that up front, then to implement this formula requires only order n arithmetic operations. So it is far more efficient to evaluate the Lagrange polynomial this way than the way it was written earlier. Okay. So, so I want to point out again, this is important to emphasize. The reason why this works so well is that the Lagrange polynomial was rewritten in a form where a large portion of it could be factored out of a summation. And then having written out Pn of x this way and then running out 1 this way, enabling us to cancel these factors that are expensive to evaluate, led to this simplification. So now and then, writing your expressions in a different form could lead to substantial improvement in efficiency. So, any questions about what we've seen here? Well, I actually covered everything. This is all that I had to cover today. That worked out well. I could have done without the half hour of wrestling with all this stuff. But that means we have a good amount of time for any homework questions. I really am going to get the grading homework within the next few days. Oh, I'm looking in the chat. I mean, they haven't asked me any new questions, but if you got them. Okay. 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 This? Okay. All right. So what I'm gonna focus on here, I guess, is how these formulas come about. Okay. Because so there are two main ideas here. Okay, so I'll focus on this first one. So we need to be equal to 1 at this point, 0 at all the others. Now, this polynomial is of degree 3. So a polynomial degree 3 can be, in general, degree n, can be determined almost entirely by knowledge of its n roots. Because once if you know what the n roots are, then you know that the polynomial is equal to this times the scaling factor. So that right there, so these three conditions, so in other words, for the j polynomial, xi with I not equal j, those are the roots, that's where that part comes from. So now, if you've gotten this far, then it's like, okay, now I got to make sure it's equal to 1 at this point. And in general, it will not be. So whatever you would get from plugging in this x value, cancel it out. So that's how you can guarantee that if you substitute this x value into this whole fraction, yes. Yeah, because what happens is, from a factorization, you have this. So what would you get if I plugged in x equal -1? Well, now I'm going to get -1 - 0, -1 - 1, -1 - 2. And I want the whole thing to be 1. So whatever I got up here from plugging in this x value, put it down here to cancel it all and get 1. Yes. Yeah, yes. Yeah, and so then in a general formula, like if you substitute x equal to xj, then you see that this factor and this factor will just cancel. So that's why the whole thing will become 1. So a polynomial of degree n is going to have a total of n plus 1 degrees of freedom. And normally think, oh, those are the n plus 1 coefficients. That means really there are all kinds of sets of n plus 1 conditions that you can impose. And that's what was done here to determine the polynomial completely. Another way to think about it from a linear algebra point of view, here I've have these coefficients times the polynomials, the monomials, 1, x squared, x cubed, and I set up a system of equations. But really, I could have had these coefficients multiplied by any 4 polynomials as long as they are linearly independent, and then I would still get a system like this, where instead of having 1 x squared, x cubed, I have whatever polynomials that are multiplied with here evaluated at x0, x1, x2, x3. So by choosing the Lagrange polynomials that are equal to 0 in most cases, but 1 in these cases, it has the effect of making this the matrix of this system, the identity matrix. Therefore, the system is easy to solve because the unknowns, a0, a1, a2, a3, end up being just the y values. So it takes the whole solving a system of equations thing out of the picture. Check on the chat. Oh, okay, nothing new in the chat. Or anyone who needs to in the WebEx meeting can also unmute themselves and shout out a question if they like. Yeah.
Yeah, it was.
Okay. Yep. Right. Yeah. Yeah.
How would you describe it?
Oh, the range of allowed exponents. Yeah, that only those orders of magnitude are supported. That's all. Yep. I go ahead and check what's going on in Canvas. In other words, how much grading will I be doing this weekend? Okay. 12 people have turned in homework 1, the MATLAB. 14 people have turned in the quiz. So Hopefully those numbers will increase. Well, I took a look at how the like in the syllabus, how the grade is laid out. Homework is well, homework includes both the explorations and the quizzes. All of those items are weighted equally. So that means that since there are 10 homeworks, I believe there are 9 quizzes. So a single assignment counts for roughly, like I guess, a little more than 1.5% of the overall grade. So if assignment's not done, I would not call it a disaster, but if you have too many of them, although one thing I checked here, you know what? Okay. I had meant to do something about the like dropping a lowest or something, but it's not mentioned in the syllabus. But I I will drop the lowest of the exploration assignments. So, okay, so really very 30 over 18. So okay, so um, mm, yeah, so your assignment is 1.6 repeating percent. Okay, is there a question in the chat? Okay. Oh, okay, yeah, but okay, question in the chat about the quizzes. Okay. Yeah, sorry, I should make that clear in the syllabus that um that the um that quizzes belong from a purpose of determining the overall grade. Quizzes fall in the homework category. So yeah, unfortunately, the name of a category in the syllabus says simply homework. That should include quizzes too. So I will edit that. Oh yeah, yeah, that's the thing. Unfortunately, yeah. So what I've been meaning to do is, if I get a question like by email that is of general interest, like for instance, if it would not give away a person's answer, then I would post it on the site. So, well, I haven't been getting many email questions, but I still need to do that. But yeah. Oh, yeah, that's how I keep track. Yeah. Okay. Well, all right, but I guess you have a good chance of getting a point. Yeah. Yeah, especially if it's something like something that could be clarified about the question. Okay. Um, yeah, okay. Yeah, hold on. I'm uploading a corrected syllabus. What? Oh, okay. Courses. Okay, actually, I want to take a look at my files regarding the tests. Okay. Okay, so as far as material is concerned, okay. I'm going to return to the notes so I can put this information in there. Unfortunately, typing in this thing, my display's all wonky here. Okay. So first, okay. Make this browser window bigger so I can see what I'm doing. Okay. Look at the schedule. Okay, so the midterm exam is, okay, so October 14th. Okay. And then, okay, so October, so the class period for October 12th will be entirely about a review. Okay, so the coverage on it. So by then, I will have covered up to section 7.5, it looks like. Although I'm not certain if I'm going to, because that's something I cover right before the review. Okay. So as far as how I'll go, okay. Yeah, I'm not going to go that far. Okay. So actually, we're almost finished covering the material from the midterm. Okay. Because I just finished 7.1 and 7.2 today. There's still 7.3 coming up next, and it's 7.4. So I will be covering 7.5 before the date of the midterm, but there will not be a midterm question on it because you would not have had a chance to do a homework on it by then. Okay, and actually, if I take a look at what's happening with upcoming homework assignments and what they cover. Okay, so you're doing 2.1, 2.2. Okay, so that would amount to homework 4, it looks like. Okay. Yeah. Sorry, I'm checking a bunch of things on the website just to make sure I'm giving you all accurate information. Okay, so homework 2 is on 2.1, homework 3 is on 2.2, homework 4 is on 7.2, homework 5 is on 4. Okay. Okay, so that's actually material on homework 5. Okay, now, so what we'll be doing soon is, no, I don't want those question marks. Okay. There will be a practice test posted. So sometime next week I will have that up. And for a practice test, I will also post a solution. So this will give you an idea of indicate so what you can take away from the practice. First of all, how many problems? Our content areas, like what topics will be covered. Okay, but not the particulars of problems. So substantial details will change. One thing I do this in a lot of my classes, certainly undergrad classes, and one thing that kind of aggravates me is when I put out a practice test, go over that, then the real test happens, and some people will simply repeat the practice problem, and that's not going to get you many points. Actually, hardly any, because the problem has changed. So please keep that in mind. That there are substantive changes from the practice of real, but the practice is meant to protect you against surprises. I never want to have a situation where a student comes out of a test thinking, wow, that was nothing like what they could have expected. So this should take care of that. Okay. So plenty of information will be forthcoming. Now, one thing to keep in mind, though, is when I look at the schedule, actually looking at the practice test, the last section that I actually have is actually not 7.4, but rather 7.3. And that section I will be spending all of next week on. Now, the homework corresponding to that section and the next one is not due until after the midterm. But you're just going to see like a midterm problem for practice, and so you can focus on that, even if you don't get around to the homework yet. But there's also good reason to try to keep up with the homework, even though I'm relaxed about due dates. Yeah, it looks like I have to fix something in Canvas here. Let me check. Okay, yeah, I have unfortunately separate under assignments. I have separate categories for homework and quiz, and they really should be in the same category. So I am fixing that now. So that way the quizzes will show up in the grade book. Yeah, I think I used to have them in its own category, but I changed that later. Okay. Let's see, it's 6:43. Other questions from anybody? Okay, I will stop the recording here. But I'll stick around for any questions.